Let's continue with electrostatics. This would be lecture 4th of electrostatics, right? So let's start. Yeah, last time we studied Gauss law, right? If I could just have a look. Yeah. Last time we studied Gauss law, we did some questions. Uh, uh, First of all, we applied Gauss law to some symmetrical bodies. Then we did some questions in which the symmetrical bodies had some symmetrical cut. Is it okay? Symmetrical cut, I'm saying. So in those scenarios, Gauss law can be applied for the whole body as well as the portion which has been cut out. Remember that cylinder wala question, a cylinder out of which a sphere was cut. Is it okay? So just a second. Yeah. So uh, the Gauss law portion has otherwise been finished, but I would just like to discuss two problems, okay, to put a little bit more light on the flux thing. So the first question we have here is, now this is a hollow sphere, okay, out of which, what is this? This is a infinite line charge, okay, charge density lambda, it passes through, the distance, the radius is r, the distance is x, the distance of line charge from center is x, okay. You have to find flux through sphere, okay. The sphere was neutral, this is one question. Another one is same hollow sphere, neutral. Now this time a sheet is passing through it. This is a sheet. Okay. Now this time a sheet is passing through the same sphere, same, everything is same, the distance is x, this is r, and this is infinite charged sheet. Charge density sigma, again you have to find flux. Through sphere. Answers, anyone? Anyone from online? On. So let's start with the first one. I hope that you would be able to do the second one after that. Now the portion of line charge that is included, let's call it L. L length of line charge has been included into the sphere. Is it okay? So the charge enclosed would be how much? Lambda into L. यही होगा ना. The charge inside the sphere would be lambda into L, only this much portion. So flux would be how much? By Gauss law, Q enclosed by epsilon naught, sorry, which would be lambda L by epsilon naught. Now how to find L? We didn't find L yet, but you know this would be R, this thing is X, okay, angle is 90. You can find the length of chord, it is a chord, right? So the length here would be how much? Under root R square minus X square, okay, under root R square minus X square, and the length of, total length of chord would be twice of this much. So the answer would be 2 lambda under root R square minus X square by epsilon naught. You have studied circles in 10th or 9th? Circles in which you studied chords, length of chord calculate karna. It was in 9th, some properties of circle. So that this is the same thing, right? You need to calculate the length of chord. Now this time, this one is a little difficult. It is not a line this time, it's a sheet. So some part of sheet would be enclosed. You can assume it to be cut and enclosed. So how would that look like? This you need to imagine. Disk, exactly. So this portion of sphere would be, this portion of sheet would be included in the sphere, okay? It would look like a disk which has radius this. What would be the radius? This is R. So the radius of the disk would be how much? Exactly R square minus X square. Let's call it capital R. So the area of disk inside you can calculate, and the charge inside would be how much? Sigma into area. Okay, this time the charge density is surface charge density, sigma. So sigma into area, which would be how much? Sigma into pi capital R square. Sigma pi small r square minus X square. And flux would be how much? This upon epsilon naught. Not that difficult, I guess, right? Wow. You got it? Okay. So I'll erase now, and we'll start with potential energy and then potential. Okay. I'll erase the left half. If anybody is copying, please continue. Do it quickly. In fact, we should be writing electrostatic. Okay, electrostatic energy. What is electrostatic energy? Oh, you have this system of charges, some charges Q1, Q2, Q3, Q4 and so on. Okay, so electrostatic potential energy is the amount of work done in assembling this system after bringing all the charges from infinity. You do remember this? Okay, so the work done in bringing all these charges from infinity to these positions is called potential energy of the system. Okay, so we need at least 2 charges to have a system. Is it okay? Single charge won't make a system if there is no other charge, no electric field. So when you bring a single charge from infinity to this point, no work is done. because there is no force acting on it. No force acting on it, so you don't need to apply any external force as well, right? So first charge is always brought without doing any work, then second charge would be brought by doing some work, third charge would be brought by doing some more work, because already there are some charges. So this is the potential energy scenario, you know it. For two charge system, you already know the potential energy would be how much? Two charge system, Q1, Q2, the separation is R, the potential energy is how much? K Q1 Q2 by R. This you already know, right? Not, I won't be deriving it, I won't be explaining a lot about it, because you know it. We'll apply it directly, okay? For multiple charge system, what we do is we form pairs. First pair would have potential energy K Q1 Q2 by R12. This pair would have potential energy, this is 1 2, this is 1 3, K Q1 Q3 by R13. This pair would have this pair. So total energy of the system would be what? Energy of each pair added. Okay? Is it okay? I'll erase this one. Now, let's do a little some questions, a little bit work on what is electrostatic potential energy, so that we can apply it on good examples. Okay. Now, since it is a form of potential energy, so it would be a part of mechanical energy system. There are two parts of mechanical energy system: potential energy as well as kinetic energy. And you know, potential energy has so many types: electrostatic, gravitational, elastic, and so on. Even kinetic energy has two types, don't you think? Translational and rotational, right? So we, whenever I see electrostatic potential energy, the type of question which I would see would be from you can say conservation of mechanical energy front. Okay. And one of the most asked question is closest distance of Roche. So before we start doing some questions, let's do one question like this. Before doing elaborate difficult questions, let's start with easier one: plus Q minus Q minus Q. Okay. Now you have to find PE of system, and please take care of all the pairs. Now if you remember, these are 4 charges. Number of ways in which we can select 2 charges out of them is how much? Number of ways, this maths, yeah? 4C2, exactly. We can select 2 charges out of n charges in how many ways? NC2 ways. So the number of ways would be how much? How many? 6 ways. So there would be 6 terms. Getting my point? If we have n charge system, then we can select 2 charges out of n charges in NC2 ways, which means that our potential energy term would have how many terms? NC2 terms. Obviously some of them would be 0, some may cancel each other and so on, but in total the terms would be NC2. So we would have 6 pairs: first pair, second pair, third pair, fourth pair. 4 pairs are there. 2 pairs are left. Which 2? The diagonal pairs. Yeah, exactly. This pair and this pair. So please continue. Huh? Oh, sorry. You can take side as A. Okay, it is a square of side A. it's 2. So the first pair would have potential energy k q square by A. The second pair, okay, I'll redraw because this is a little crowded here right now. So this is the first pair. The second pair is this, for which the potential energy would be minus k q square by A square by A, sorry. Okay. The third pair would be this, again minus k q square by A. For the fourth pair, the energy would be this, plus again because both charges are negative, so minus q into minus q. So this would be plus k q square by A. Okay. Now first diagonal pair, these four would cancel each other actually. For first diagonal pair, the distance between them is root 2a. So this would be minus k q square by root 2a. And for the second diagonal pair, it would be again minus k q square by root 2a. So total potential energy is minus root 2 k q square by A, negative. Okay. So let's start. See, the questions of this chapter, this topic, potential energy, would be quite similar to those you studied in gravitation. Okay, a charge is fired from this point, how far will it go, and this kind of this kind of question. Okay, the difference, only difference here would be that if the charges are similar, there would be repulsion. In gravitation, there is no repulsion. Okay, so the similar charge scenario would be a little addition to those cases which you studied in gravitation. Otherwise, the questions are exactly similar, and we'll see that even sorry, even for these cases, for this case, again sorry, escape energy kind of concept would still be applicable. Okay, escape velocity, escape energy, we'll see. So next question I would ask is, now we have three charges placed in an equatorial arrangement, in an equilateral arrangement, okay, plus q, plus q, plus q, side L. Since repulsion would be there, what would happen? They would repel each other apart. Okay. So right now the arrangement is held, it is released. What would happen? They will run apart. Okay, but they would run apart in a manner that they would still form an equilateral triangle because the charges are similar. All would move same distance and in the outward direction, right? The force would act in this direction, right? Do you remember? We did this question. This force would, force due to that charge would be like this, force due to this charge would be like this, net force would be this. You know, along circumradius, this would go in this direction, this would go in this direction. They would still form a bigger triangle. Wherever they go, they would keep forming a bigger triangle. Okay. So now the charges are released from rest. Find speed of each when separation is 2L. Okay, when the triangle becomes double in side. Okay, when the triangle has double side, at that moment you need to calculate. Correct? Shall we start? See, what happens is initially the charges were at rest, okay, and only electric forces are acting. They are conservative in nature, right? I didn't give the mass of each. Let's take mass of each particle to be m actually, because kinetic energy has half mv square. M is the mass, right? So initially the charges were at rest. The kinetic energy was 0. Okay, only potential energy was there. So by conservation, only electric forces are electrostatic forces are acting, and electrostatic forces are conservative in nature, right? So conservation of energy is applicable here. Mechanical energy is applicable here. So by conservation of mechanical energy, and this is the short form, right? So I hope it is clear to all. Initially the kinetic energy was 0. The potential energy was, for the first pair it was how much? Kq square by L, L square nahi, not square, by L. And we have one more pair, we have one more pair. In case of any confusion, always try this NC2 rule. Okay, number of pairs would be NC2. So we would have 3C2 or 3 pairs. So for each pair the distance is L. So the potential energy would be this initially. So this is kinetic energy initial, this is potential energy initial. The final kinetic energy of each would be half mv square, and since we have 3 charges, 3 particles, kinetic energy of all 3 would be 3 mv square, 3 by 2 mv square, right? The potential energy at this moment, when the separation is 2L, the potential energy at this moment would be 3 kq square by 2L. Kq square by 2L is the potential energy for one pair. For 3 pairs, it would be this 3 times. Okay. So let's solve. What we get is 3. This is kinetic energy final, and this is potential energy final. So what we get is 3 by 2 mv square is equal to 3 kq square by L minus 3 kq square by 2L. If you solve it, this would be 3 kq square by 2L. Okay, taking LCM and all. So this cancels. V would be kq square by ml under root. Okay, speed of each. This was easy one, not difficult, right? I won't call it JEE mains question. This was a little above NCERT, I would say. But you know how to apply the dynamics, right? Okay, is it okay? You have started knowing how to apply the arrangement, the situation, how to use the situation, how to apply conservation mechanical energy in electric cases. So let's study it in a little bit detail now, more of conservation of mechanical energy for electrical cases. So I'll erase this one. One specific case is distance of closest approach. Distance of closest approach. Right? Now, 3 scenarios. If you do remember, okay, try to recollect where you studied distance of closest approach. In Rutherford alpha scattering experiment, do you remember? Gold foil was bombarded with alpha particles. Okay, some of them were deflected with small angles. Most of them went straight. Some were deflected with small angles, by small angles. Some were deflected by large angles, and very few were actually they turned back, retraced their path. So retraced their path. In that point of time, you studied that actually what happens is that this is a fixed nucleus. The alpha particle would come in, get repelled away. So there would be a point which we call the closest distance of approach, the point at which alpha particle just stops before getting repelled away. Is it okay? So the closest distance of approach is what? Charge is there, another charge is projected toward this fixed charge. Let's call it Q naught. This is fixed. Now this charge Q1 is projected toward the fixed charge. This is moving with initial velocity V naught. Okay, mass is m. Fixed particle would be having some mass, but we don't need it because it won't be moving. So we don't need to calculate its kinetic energy and all. So initially, by conservation of energy, mechanical energy, initially it would be having some this kinetic energy, and since the distance was large, no potential energy would exist. Okay, R is infinite, very large. So K Q1 Q2 by R is the potential energy. It would be negligible. So initially this would be kinetic energy. This would be potential energy initial, which is 0. Let's say it stops here and gets repelled away. Stops here and gets repelled away. So this is the distance of closest approach. There is a scenario when one charge is fixed. Okay. So when it approaches, at this point it stops momentarily. Is it okay? At this point the charge stops momentarily, this moving charge. So the potential energy, the kinetic energy at this point would become 0, while the potential energy would be how much? K Q1 Q naught by D. You can find D obviously, not very difficult. It would be 2K Q1 Q naught by mv naught square. Okay. So this is the distance of closest approach. This indicates how close the charged particle would reach. Okay. Okay. Now this is just one isolated case. This was what Rutherford calculated. In his scenario, the charge Q naught was what? Charge on the gold nucleus. The charge Q1 was alpha particle plus 2e. Okay, I don't remember gold the atomic number of gold. I don't remember. Otherwise, I would have told you that. But for this, the charge would be 2e. For this, it would be Ze, where Z is the atomic number, right? And we could calculate the distance of closest approach, right? But this is not the only scenario. In physics, we go a little bit more into the details. What if this is not fixed? What if the gold nucleus was free to move, but at rest initially? In this scenario, we say both charges free to move. Okay? And we would discuss one more case. Questions have been asked out of this. So this is our charge Q naught, this is charge Q1, and the distance initially is very large. It is moving with the velocity V naught, mass is m1, this mass is m2, let's call it q2. Okay? The initial distance is large. Okay, large distance. Now, the point here is, as the moving charge approaches the rest charge, this was initially at rest, let me write it. As Q1 approaches Q2, because of repulsion, Q2 would also start moving, okay? And as it comes closer, it starts slowing down because of repulsion. This charge was slowing down here also. See, okay? The charge Q1 was slowing down here also. It was slowing down and it stopped here. In this scenario also, it would slow down. It would keep on slowing down and it would speed up. Okay? So what would happen? It would slow down to some speed, and it would speed up as well. There would be a time when both would be moving with same speed. ऐसा होगा. Let's say if it starts with speed 20, it would slow down to, if let's say both are identical particles. We assume that both are identical particles. It moves with 20. Okay? It slows down. It starts with 20. It slows down to 10 in the meantime it would speed up to from 0 to 10. Is it okay? Because of forward repulsion on this and backward repulsion on this. Okay, but since on this system no external force acts, can you see that momentum, linear momentum would be conserved? Okay, since both charges are moving, we need to find velocity, we need to find the distance considering velocities of both the charges, right? Considering kinetic energy of both the charges. So we need, we cannot do it directly. We need a little bit more detail. The detail is this: since no external force on system, since F external equal to 0 on system, we say linear momentum is conserved. Okay, linear momentum is conserved. What happens? That m1 v0 is equal to, this is the initial momentum of the system. What happens is, after some time, I'll draw it here. This one is moving with v final. This one is also moving with v final. And the distance between them is d. Okay, just think about it. These are two particles very far off. As the rear particle, the left particle approaches, right wala also starts moving. This slows down, this speeds up. There would be a time at which both are moving with same speed. After this, this would slow down, this would speed up further, and the separation would increase. Is it okay? Is it clear? I hope this is clear. That as this approaches, the rear particle approaches, it slows down and it speeds up. So the distance between them is decreasing, decreasing, decreasing. A point comes at which both have same speed, after which the right particle would speed up. So it will move faster, it will cover more distance than the left particle. Obviously the separation will increase. The right particle will cover more distance and the left particle will cover less distance. So gap actually increases. So it's like this covers small distance, but this covers large distance. The gap increased. So the gap between them is minimum only when they are moving with same speed. That is for just one moment. Okay, after that the gap will increase. And we did this kind of thing when we were doing that reduced mass wala concept. Do you remember? This is kind of a spring behavior. You know, in our scenario, what we did, we gave some velocity to the rear block. As it came, as the rear particle was coming, was moving, it was slowing down, and the front particle was speeding up. Same kind of arrangement. Okay, this was pushed, spring was compressed, so it was slowing down, it was speeding up. The distance of closest approach, in that scenario also we did that the compression would be maximum when both move with same speed. Please go back to the lecture notes where we studied this. In SHM we studied this, and in fact in recap classes I also discussed this thing. Okay, so the same kind of arrangement is here. The distance between them would be minimum only when they have same speed. After that, this would move quicker, so it would cover a lot more distance and it will cover less distance. Obviously separation would increase. So now this was the initial momentum. The final momentum would be this: m1 vf plus m2 vf, which would be final velocity is what? m1 v0 upon m1 plus m2. Okay, we have found the final velocity. Now by conservation of mechanical energy, initially only kinetic energy was there, the distance was large, so potential energy was 0. So kinetic energy half m1 v0 square, potential energy 0. This is kinetic energy initial, potential energy initial is equal to, now the kinetic energy for both would be how much? Half m1 vf square, half m2 vf square, kinetic energy final, plus the potential energy between the two charges. Okay. Now since the distance between them is d, the potential energy would be k q1 q2 by d. Okay. Vf we have just calculated, final velocity we just calculated, we can replace. I'll do that for you. Let me erase this half. So this would be k q1 q2 by d would be half m1 v0 square minus half m1 plus m2 v final square. Like this, replacing Vf, we get m1 square v0 square by m1 plus m2 whole square. Okay. Solving this, I won't be solving it totally. I'll directly write result. You can solve it on your own. The result would be this: half m1 m2 v0 square by m1 plus m2. Okay. So d would be how much? 2k q1 q2 m1 plus m2 upon m1 m2 v0 square under root. Okay. Since the scenario may vary for the question, for different questions, somebody is asking some doubt. Okay, I would repeat it. When both charges are free to move, what happens is, let's say this is a charge placed in vacuum, charge in vacuum, some other charge is coming from very large distance. So as it approaches, because of repulsion, the front charge starts speeding up, the rear charge starts slowing down, and the distance between them starts decreasing. Okay. There would be a time when it would slow down to a final speed Vf. It would also speed up to a final speed Vf. At this point, the distance between them is minimum. How can we say that? The reason for that is, after this, the rear charge would slow down, so it would cover less distance. The front charge would speed up, because of repulsion obviously, would speed up, so it would cover more distance. So after some time, the scenario would be like this. This rear charge reaches this distance, the front charge covers a lot more distance. So the separation now is more than d. Okay. So separation is minimum when both move with same speed. Now in this arrangement, we don't know the final speed. In the previous one, which I erased, in the previous one, the final kinetic energy was 0. Here the final kinetic energy won't be 0. And since we don't know final speed, we won't be able to calculate it. Okay. So for calculation of it, we apply linear momentum conservation. How? External force on the system is 0. Only the two forces between the charges act. The repulsion forces between the two charges act. No other force from outside region. So we say external force is 0. We apply linear momentum conservation, and we say that final speed is this one, m1 v0 upon m1 plus m2. Also, only conservative forces are acting, so energy is conserved. Mechanical energy is conserved. Initially, only kinetic energy was there. Potential energy was 0 since distance was very large. Finally, the kinetic energy would be, for first particle, half m1 vf square. For second particle, half m2 vf square. This is when the distance between them is minimum. At minimum separation, this is the kinetic energy, the potential energy is k q1 q2 by d. So I just solved, I replaced Vf in this, okay, and just found d. Yeah. Huh? Oh, sorry, I accidentally placed root. Actually, there was one square thing, so somehow, in force, this is generally d square, so that thing got into my mind. Okay. Now the third scenario in which they are not in the same line, and that's what actually came in JE. These two have come. The first never came actually. You would understand that. It was way too easy. Okay. The second case, it came in different scenarios. Okay. But way back. The third case came recently. Recent means, you know, in IIT realm, recent means like 5-6 years span. Okay. So the third case we would discuss is now. The third case is when one charge is fixed and other moves along approaches. I should write approaches through a direction other than line joining. Okay. So what actually I mean to say is, this is the charge which is fixed. Okay. Now charge 2 is approaching like this. This is m comma q1. Okay, m q1. They are approaching, so the direction of motion is like this. It's not directly trying to hit q0. Okay, the charge q1 is not directly trying to hit q1. So the perpendicular distance, let's call it r0. The perpendicular distance between the path, initial path and the charge. Okay, the initial path is along this line. Initial line of motion is this. The perpendicular distance of fixed charge from initial line of motion is r0. Okay, what happens in this kind of scenario? This is what happened to all those alpha particles which were deflected through a small angle. What happens is, as it approaches, it deviates. Okay, it deviates. So in this scenario as well, it is not going to stop. Okay, so what would be the distance of closest approach? The distance of closest approach would be this, the perpendicular distance. Okay, this is the minimum distance of charge. I have drawn the path. You can see that this is the minimum distance of charge, fixed charge from the curve of motion. This is the minimum distance. So this charge would be would be closest to the fixed charge when it is at this point, the perpendicular wala point. So at this point the velocity would be v. Obviously v would reduce because of repulsion. Is it okay? We would reduce because of repulsion. So in this scenario, since no external force acts, what can we say? Linear momentum, or does external, sorry, this is fixed, I didn't write. Actually, since it is fixed, it would be placed between two supports. है ना? It would be fixed by some support, so that support would apply force. So that assumption is wrong actually, I didn't mention fixed here. What happens is, since this charge is fixed, some force is needed to keep it here. Some external force would be needed to keep it fixed here. So the external force is non-zero. So we cannot apply linear momentum conservation. We can still apply energy conservation, but v is not known and this perpendicular distance r is not known. We have two unknowns and we have just one equation, the energy conservation. We need one more equation. Out of mechanics, one more conservation law comes. Do you remember? We had three. The first one we studied was conservation of mechanical energy. Second one was conservation of linear momentum. And the third conservation law which we studied was conservation of angular momentum. Okay? If net external torque is 0, angular momentum is conserved. So the force let's say the particle is right now here, the force between them are directed along this line. Okay, if we take q naught, if we take q naught as a reference point, the torque would be 0 about q naught. Is it okay? So linear momentum would be conserved about q naught. Do you remember this? या ज़्यादा time हो गया है? Is it that long? Huh? Do you remember this? That since tau is equal to 0 about q naught, angular momentum is conserved about q naught. Okay, let's apply. You got my point here, that since the energy is conserved, since conservative forces are only acting, and we can one thing which we can, one conservation law which we can use as energy conservation, another one would be angular momentum conservation. Okay, even in gravitation based questions same thing applies. One question is that I'll just frame it. This is a random question. A charge, a particle, some particle is projected from Earth at some angle. This is projected. This is the normal direction. It is projected at an angle. How far from the Earth's surface will it go? Obviously, it would go like this and fall back. The velocity is not small. It is large enough. We can say it is v. Do you remember orbital velocity was root gr? So it is same as orbital velocity or less than orbital velocity. Okay. The particle goes away and falls. So the question asked what is the perpendicular distance between them, and this is an actual JEE question. Same thing applied. Okay. What? About this point, angular momentum was conserved, and kinetic energy and mechanical energy was conserved as well. So this question was solved using these two concepts. Linear momentum was not conserved. Why? Because the particle was changing direction, and we are assuming Earth to be fixed. Okay, we are assuming Earth to be fixed. So linear momentum conservation was not applicable in this case. So this is actual JEE question. This kind of question has been asked as well. I will erase this. Now let's apply by conservation of angular momentum. Initially, the direction of motion was along this line. Okay. Do you remember that actually angular momentum was written like this, mvr perpendicular? It was r cross mv, out of which through cross product we used to write r sin theta, then this was r perpendicular. Okay. What it actually meant was that if the particle is moving along this line, r perpendicular is this distance, the perpendicular distance of line of motion from the reference point. Is it okay? Do you remember this? Okay. Do you remember rotational a little bit? So I'll just explain a little bit. If even for torque we used to apply this. If this is the reference point, force is acting like this. What we can do is, to find it in a easier manner, just extend the line of action of force, drop a perpendicular. This is r perpendicular. So if the force is acting at this point, same torque. If the force is acting at this point, same torque, because the perpendicular distance is same. Okay, as long as force is acting on the same line, the torque would be same. Same applies to angular momentum, right? So I'll erase this one as well. What I'm saying is, since the particle was coming in this direction, the perpendicular distance would be r naught, perpendicular. Okay, just extend the line of motion and drop a perpendicular. This is the perpendicular distance. So initial angular momentum would be m v naught r naught. Okay. At this point, the perpendicular distance would be how much? R, and velocity would be v. So the final angular momentum would be mvr. We don't know v or r both. Okay. Let's first find r. It would be m cancels. V naught R naught upon V. Let's find, sorry, V naught, let's find V first, because we need to find R, the final distance actually. Okay, I'm finding V first because we need to find R, the distance of approach, closest distance of approach. This we need to find. So I am finding V, uh, and I'll put it in some other equation. Which is the other equation? That is conservation of mechanical energy. Okay, this is half m. Initially the kinetic energy was half m V naught square. Potential energy was 0. The kinetic energy at this point of time when the separation is R, at this scenario, the kinetic energy is half m V square, and the potential energy is how much? Because of the R distance, it is what? K Q 1 Q naught by R. Is it okay? Replace V here. What we get? Half m V naught square minus half m V naught square R naught square upon R square is K Q1 Q2 by R. Okay, this is this. Okay, so if you solve it, it is what? It is a quadratic in R. This is R square, this is R. Quadratic in R. Obviously I can solve it right here, it will take a lot of time. So since the values of m1, the values of mass, charge, R naught, they are not given here or are not related even. Okay, the values of charge q1 and q2 are not related, the values are not given also. So the so solving this would actually be a little difficult, time taking, not difficult exactly. This would give you a quadratic equation. Sorry, this is plus sign. This would give you a quadratic equation in R. Okay, which can be solved to find roots. So there would be two roots, and out of which one root would come out to be one. For one, the distance would be negative. One root would be negative, one root would be positive. So the positive root gives the final distance, the closest distance actually, the minimum distance. Is it okay? I am not solving it any further because it is dependent on a case-to-case basis. You know, generally the values are given give to be very simple. They just check that can you apply this and can you apply this actually. Okay, can you apply these two conservation laws correctly? They just test this. The values given are generally simple, and that's why the answer can be found. Answer here can be found. It will take a lot of time. So I'll write here. This is a quadratic equation in R, comma, roots of which will give R, or closest distance of approach. Okay, so I'll just go through it. Okay, I'll erase it in a moment. So shall I erase it? Okay. This thing would have gone little over the roof, but this is not difficult. It is just that we generally forget what? The third conservation law of mechanics, which is angular momentum conservation. We don't remember it. And this fact is exploited by the exam. They give questions on which angular momentum, in which angular momentum conservation is valid, is used. Right? So I'll give one question, not related to this one. Okay? The question is this: a charge plus q is fixed here, a charge plus q is fixed here. This line joining. A charge minus q is here. It is given velocity u in perpendicular direction. Okay? The separation here is a, and here also a. Okay? The charge minus q is given velocity in perpendicular direction. What happens is it goes forward, stops somewhere, and comes back because of the attraction. Okay, one charge is positive, one is negative. So what happens? There is some attraction between the two charges, between the two pairs rather. So because of this, it stops. So you have to find this stopping distance. It's not. Shall we start? Shall we start? Let's assume that it stops when the distance is s naught. Initially, when the charge comes here, okay, initially the kinetic energy, you can well understand that it is just a question of what? Conservation of mechanical energy, right? Okay, and since these two are fixed, no linear momentum conservation. Okay, angular momentum conservation is also not applicable, because if you take this as a reference point, the forces on this would produce a torque and so on. Okay, so only conservation of mechanical energy is needed. Actually, this is the simplest possible question, just one conservation law needed. So what happens in this scenario is, initially the kinetic energy was half m. I didn't give mass m, I hope you have assumed. Okay, initially the kinetic energy is this. Okay, the potential energy between first pair is minus k q square by a. Okay, between this second pair is again minus k q square by a. So I write 2 here. Okay, this is ke initial, this is pe initial. Finally, when this charge momentarily stops at this point, this pair would have potential energy, kinetic energy would be 0, right? Ke final would be 0. It stops for a moment. Okay, after that, at that point, the potential energy would be how much? K negative sign के साथ minus k q square by under root a square plus s naught square. Okay, and since there are two pairs like this, so I would place minus 2. Okay, so how to solve this? The left hand side has no variables, they are all known quantities, so it's not a quadratic or some difficult kind of equation. What you need to do is just transfer this portion there. Okay, transfer this portion onto the left portion and reverse it. Okay, so it would be how much? Mu square by 4 kq square minus 1 by a is this is minus, this is plus 1 by under root a square plus s square. Okay, like this. Okay, so what can be done is you can take LCM on the left hand side and take invert and square. Is it okay? So the question is a little lengthy, but again not difficult. Okay, cross multiplying and squaring we get this value, and transferring a square on the other side and taking under root. Obviously, if the value of u was given, if the value of u was given earlier, or some numeric values would have been given, this quantity would have become a lot simpler to solve, right? So I would be leaving it here, since this is only a mathematical question now. Where is the duster? Okay, since it's only a calculation based question now, no concept application, I'll be leaving it here. Okay, you can try it on your own. So the next thing we would study is electric potential. What is electric potential? What is electric potential? Yes, yes, exactly. Amount of work done in bringing a unit positive charge. It is applicable for positive, right? Unit positive charge from infinity to that point. So to that particular point. So it is applicable for a particular point. Is it okay? Different points would have different potentials, even though there is no charge at that particular point. Is it okay? You need not have, just like in case of electric field, you need not have any point, you need not have any charge at a point to find the electric field. Is it okay? Point clear hai? You need not have any charge at a point to find the electric field at that point. Same way, you need not have a charge at particular point to find the electric potential at that point. Is it okay? So electric potential is what? It is work done in bringing a unit charge, unit positive test charge from infinity to P point. So infinity to P point, we are bringing a small charge plus Q naught. Okay, plus Q naught we are bringing. Let's say the work done is W. Okay, so potential would be what? W by Q naught, and with the condition that Q naught should be very small. Why? Because if Q naught is large, it may disturb the charge distribution. You know, what if some conductor is placed here? If a conductor is placed here, if we bring large charge here, it will repel the positive charges to the other side. Okay, not very helpful, right? So for a point charge, let's try to find. Okay, this is infinity to P. Okay. For point charge, you already know. What is it? Hmm? How much is the potential for point charge? KQ by R. Is it that difficult? नहीं भूल गए क्या? How do we find? Actually, at infinite point, I'll explain it. Work done पहले find out कर लेते हैं. Work done from here, taking the charge from here to here, would be what? Difference of potential energy between these 2 points. How come? Do you remember there was one thing called work energy principle? What it used to say? That work done, not exactly, in potential energy. In potential energy, what you studied in last year was that the work done by a conservative force is stored as potential energy. Okay. So the change in potential energy in this procedure is the work done that you are doing. Is it okay? Okay, change in potential energy, because this is what we did. Work done is stored as potential energy, right? So from taking the charge, for taking the charge from here to here, this much is the change in potential energy, and this would be the stored, this would be, this energy would be supplied by what? External forces and all. Okay. So this you already know, at P point the potential energy would be what? K Q Q naught by R. If we have a point charge here Q and a charge Q naught is brought from infinity to R distance, the potential energy would be at infinity is 0. So work done is this, potential would be what? This divided by Q naught, and taking the limit. Is it okay? So this you already know. I hope that I thought that I would not be teaching all this. Eh? I thought that I would not be teaching all this. I would just be telling the formula and I would be continuing. Okay, हो गया. But चलो कोई नहीं. Now, when there is a charge distribution, this is for point charge. For charge distribution, what we do? We find a small charge. Okay, we find a small charge. Take a small charge dq. We try to find, this is the point P, the distance is r, this is dq. We try to find the potential due to this small charge. The potential due to this small charge would be this, and what we do is integrate. है ना? So you still remember that the linear charge density was lambda, the areal charge density was sigma, and the volume charge density was rho. This is one way. We would learn one more way, okay, in some time. After that only we would start finding potential for different bodies. Is it okay? So please go ahead with it. I'll erase the other things. Now, a relation between V and E vector. Do you remember this? क्या होता है? Minus dV upon dr. I'll modify it slightly. Okay. In NCRT, actually, in most of the cases, potential is expressed in terms of R. What if it is expressed in terms of X, Y, and Z? We do a question of this as well. But just check. Somebody is asking a doubt. Electrostatic potential energy and electrostatic potential. See, electric potential, just somebody asked this thing, what is the difference between electrostatic potential energy and electric potential? First difference is electrostatic potential is defined for at least two charges. Electric potential can be defined for one charge only as well. Is it okay? So electric potential is a way of expressing field. Okay, you know field, we studied field, electric field. One way of expressing electric field was using vector way, that was electric field intensity E, which we were doing earlier. One other way of expressing it is in a scalar way called electrostatic potential. Okay, why two ways? The reason for that is there may be points where field is 0. So if field is 0, we would think that actually oh the field everywhere is 0. You mean this gives an impression when field at a point is 0. This gives an impression that if you bring a charge from infinity to this point, you would not need any work because the force at infinity is 0. The force at that point is 0. You won't be able to get any work done. You won't be able to do any work done for this duration. Okay, the potential gives us a picture of work done. Okay, at points where field is 0, potential may not be 0. So what we get is if we bring a charge from infinity to this point, the work done would be positive or negative, whatever the case may be. Okay, it won't be 0. So apart from field which gives us the direction in which a charge would be pushed or pulled and the amount of force, field gives us an indication of the amount of force acting on a charge. Okay, potential gives us an indication of amount of work done that needs to be done in bringing a charge from some point to this point. Is it okay? So these are two different aspects of field. Okay, potential is an indicator of field, while potential energy is an indicator of the arrangement, how the charges are arranged and the interaction between them. Is it okay? So potential can be of only one charge. Okay, but potential energy would always be of at least two charges. Is it okay? I hope this is clear. Okay, please write big letters. I am really sorry to whosoever has a problem. Now relation between V and E. Now this you have studied already in NCERT, that E is what? Minus dV by dr. Okay, this works when V is expressed in terms of R. What if V is expressed in terms of X, Y and Z? So I'll slightly modify this. This is called del operator, del V by del R, and this can give us a vector quantity. How? This actually expands in this form: del V by del X I cap, del V by del Y j cap, and del V by del Z k cap. Okay, okay. And do you remember? Have you done partial derivatives? This is a thing of the past. In work energy power, this was introduced. This would have been introduced. If not, then it's very easy to understand. Partial operator means when V is a function of X, Y and Z, three variables. For this portion, you will assume Y and Z to be constant, only X to be the variable. For this portion, you need to assume X and Z variable and so on. So let's have a question on this. Let's have a question on this, and then we'll move further. Now, the potential in a region is given by minus kxy. Potential is given as minus kxy. Z is 0. Okay. Okay. A charge M is placed at a point 2, 1. Okay. A charge M is placed at a point 2, 1. So because potential exists like this, electric field would exist, and because of electric field the charge would accelerate. The charge, slight difference, this has mass m, the particle has mass m and charge q. Okay, particle of mass m and charge q is placed at this point, 2 comma 1. The potential in this region is V is equal to minus k xy. So electric field exists in this region. Okay. So you have to find initial acceleration of charge q. How to find it? I'll give hint. Find electric field, find force, then you can find A. Shall we start? Let's see. Electric field is given by this. Okay. Our potential is minus k xy. So this minus and this minus would cancel. Actually, final would be plus. The result would be plus. Now let's differentiate. When you differentiate V with respect to x, y remains constant, ky would come out. So what I am trying to do here is, let me erase. I am saying that del V by del x would be how much? Minus k xy. Okay. K and y are constant because we are differentiating partial differentiation. We are doing partial differentiation with respect to x only. So this would be minus ky del x by del x. Okay. Derivative of x with respect to x is always 1. So minus ky. Similarly, for y, differentiation with respect to y, only this part gets differentiated. Kx would come out. Is it okay? So the electric field would be this. The force on the charge would be QE or minus, or sorry, not minus, plus KQ y I cap plus K plus x j cap. Okay. The force is this in vector form. Okay. Since the force is this, you can see force is dependent on y and x. So force at this point would be how much? Force at this point would be 2 I cap plus, no sorry, y was 1, sorry, 1 I cap plus 2 j cap, x was 2. This is the force and acceleration would be how much? This upon m. Bas? This was the question. Okay, shall I continue? So the relation when V is given and you need to find E, this is the relation. Let's go in the reverse way. Okay. You know that E is, I am writing this Y. Let us assume that V is given in terms of R. Okay. When V is given in terms of R, this holds true. Okay. Because there is no other variable. Why we were doing partial differentiation was because we had 3 variables x, y, z. So at one point of time we could differentiate only one. Now if only one variable R is given, this thing as well as this thing are same. Okay, there is only r, v has only r. Okay, the terms v has only r which can be differentiated. So if you differentiate it in the partial way or in the complete way, it gives us the same result. So I am expressing it in this manner. So dv can be expressed as e dr. Okay, and if we express it in vector form, it would be what? Minus e dr. This was minus sign was there. Okay, okay. Why? Because if you remember that this used to give us a vector quantity. Okay, so whole of this quantity was vector. Not dv was not, this del v was not a vector. You know, potential is a vector quantity. Whole of this was vector. Okay. Now if we multiply these two quantities, E is a vector and dr is another vector. You can do it in two ways, you do remember, right? And potential is a scalar, so we opt for what? Dot product. So dv is minus E dot dr, and you know, if we integrate both sides from point A to B, this also point A to B, what we get? Here we get potential Vb minus Va is minus integral E dot dr. Okay. So if we know electric field, we can find potential in this manner. Okay. This is what? Potential difference. This is what? Potential difference. I'll write it here, otherwise. Okay. So potential difference can be expressed in terms of electric field as this. If point A is at infinity and point B is at whatever point P you are taking, okay, what we are doing is we are taking A at infinity. Okay, we are bringing a charge here at point P. The potential difference would be what? Vp minus V infinity, and you already know that V infinity is 0, right? So for B tending to infinity and P and A is equal to P, Vp is equal to minus integral infinity to P. Okay. Sorry. What I am saying, what I wrote here is, if we take, you know, this gives potential difference between 2 points. Is it okay? If I place one point at infinity, the potential for that point would be 0. So potential difference would actually be equal to the real potential. Is it okay? At point P. So by placing one point at infinity, we can find actual potential. Okay, same formula, but the limits now are from infinity to P. Why we did this? Because we now have two possibilities of finding V. How to find V for different bodies? Huh? The minus sign is here. कहाँ पे? ये? Actually I took, okay, I made a mistake. I wrote A at infinity, but this should be the scenario, I'm sorry. In the diagram, I took A at infinity. Everything I wrote in terms of A, but just I mixed these two. So the point A is at infinity, B is our point P, where we need to find potential. Potential at A would be 0, at B would be the potential which we need to find. Why we were doing all this? Because now we have two methods of finding V. One is find dV. If E, formula for E is difficult, then what we do? We find dV and integrate. Okay, but if formula for E is easy peasy, right? what we do? We find potential in this, using this scenario. No need to find, take dq, then find the principal, then find the small amount of this potential and all. This was infinity and this was p point. Is it okay? Is it okay? Let's take the examples now. We would actually calculate the examples, but let's take. You know, E was really difficult to find for disk, very difficult, right? So E is difficult for, E is difficult for what? A disk? Hmm? याद है या do you remember or not? Like for in our case, let's start from very basic thing, a point charge. For a point charge, the formula of E is very easy, kq by r square. You can simply place it, find V. No need to find the work done and dash dash dash. So applicable for point charge, right? The next thing which we studied was what? A ring. Formula difficult hai thoda, a little difficult. Okay. Since E, the formula for E of a ring is difficult, we will calculate ring using integral dV. Okay. For a disk also, integral dV. What about a sphere? For a hollow sphere, field outside was kq by r square, okay, and field inside was 0. Both are easy, right? You don't find 0 difficult, right? Okay. So field outside was kq by r square, field inside is 0. Easy formula. Okay. Let's, since E is easy, we use this to find potential for hollow sphere and even for solid sphere. Okay. Okay. So these are the relevant bodies for which we'll find. Okay, let me check this. There can be that rod वगैरह हम लोगों ने किया था, line charge and all. Okay. For line charge, what? The formula is difficult or easy? Hmm? For line charge, 2k lambda by r. That's easy. You can solve it here. Okay. We'll find a little problem in that scenario because one value is infinity. One value is infinity. So, but still easy. We can find, if not V, we can find potential difference for a line charge. We'll find in the real scenario why V is not defined for a line charge. Is it okay? So this is easy for line charge and so on. So even though formula looks difficult, it applies to a lot of bodies, and this one looks easy. It applies to only 2 bodies, right? So this part, it appeared very difficult, pata nahi kya ho raha hai, type of, right? So this part is actually easy. The effort which we put in here pays off in these scenarios when we calculate this. Okay. Even for do you remember dipole? Even for dipole, we can solve it using these formulas, using this formula E. Okay. So I'll erase all this. So before we proceed further, I just taught potential difference. Did I? Just a second. I just gave a reference of potential difference. Okay. Heading wise, I'll just write. You already know potential difference is what? Delta V is what? V B minus VA, or you can write it as VBA as well. Okay. Okay. If you remember, This is what? Work done from infinity to B upon Q naught minus work done from infinity to A upon Q naught. This is a limit Q naught tends to 0 applies to both. So, this is infinity, you are bringing a charge Q naught from first you brought it from infinity to point A, then you brought it from infinity to point B. Okay? Okay? The work done, since work done is a scalar quantity, so work done, the difference of these two work dones would be how much? Work done in taking the charge from A to B. Is it okay? We are doing what? We are subtracting these two work dones. Is it okay? We are subtracting these two work dones. So the subtraction, the result of this subtraction would be what? Work done from point A to B. Is it okay? So you can write it as limit Q naught tends to 0, work done from A to B by Q naught. This is VBA. For our convenience, for practical purposes, what we say, if potential difference between two points is given, what we say about work done? The work done would be what? Q into the potential difference. I will write it here. If a charge Q is taken from A to B, work done would be how much? Q into VB minus VA. Okay, this can be used other way around. This can be used other way around. Karan, shall we do? A continuation to this. Let's say there are two plates between which a V potential difference exists. Okay, let's say this is positive, this is negative. A point charge plus Q is released from here. It's released from here. What happens? Negative charge attracts, positive charge repels. It travels, let's say this distance is d. It travels through this distance. Okay. So the work done on positive charge would be how much? Would be how much? QV. Is it okay? The potential difference between these 2 points is how much? V. It is V. So work done would be how much? QV. Is it okay? And this work done QV gets converted into the kinetic energy of the positive charge. So this would be half m V square. You can find the final kinetic energy. Is it okay? Is it okay? So this kind of thing will be used a lot many times. I'll mark it as star mark. Okay. This will be used a lot many times when you study modern physics, right? In those scenarios, you would study that a charged particle is accelerated through 200 volt potential difference. So when let's say an electron is accelerated through 200 volts, its kinetic energy would become 200 E QV. Going by the logic QV, its kinetic energy would become 200 E, where E is the charge of electron. You can put the value. So the velocity at end of this 200 volt at the other side would be how much? You can find. Is it okay? So this thing is very quickly, very frequently used. This thing is very frequently used in modern physics. So instead of teaching it there, I just introduced it here itself. Is it okay? So I'll erase now. Let's start finding potential for different cases. For a point charge you already know, okay. I need not explain, it is kq by r, okay. For, let's first find for a rod, finite rod, okay. It's not infinite, it's finite rod, and we are taking an axial point. First one is axial point, okay. Second would be what? Equatorial point. You can solve it on your own. I'll just explain what, how, okay. I won't be, this would be homework, you can call it. Equatorial point, this would be axial point, okay. This is a rod of length L, okay. You need to find potential. The charge Q is spread uniformly over the rod, okay. You need to find potential at point P. So now do you remember the formula for this kind of scenario was actually not so easy. It was difficult, right? So our approach would be what? Finding dV. Remember, when E is tough, you find dV and integrate. When E is easy, you find integral E dot dr, okay. You find integral E dot dr. So for small portion, let's say this distance is a, you take a small element dx, okay. The charge density would be how much? Q by L, charge spread uniformly, okay, which is actually equal to dq by dx as well. For small portion also, the charge density would be same, linear charge density. We studied this earlier when we were doing the chapter, the questions, starting portion. So this would be lambda dx or q by L into dx. So due the small charge dq is what? Q by L into dx. Is it okay? For small charge, the value is q by L into dx. For small charge, the potential, let's say if the distance between x is, between the charge and the point is x, the potential would be how much? dV would be how much? K dq by x, okay. Okay, you do remember that what we did the other day, 2 weeks back. What we did? We assumed that at a distance x from point P, there is a small element dx, okay. We found the field due to that. Similar way, we are finding the potential due to this small element at P. The potential would be k q by L dx by x. You see dx by x form ln, okay. Log, integral would be log. So the potential would be what? Integral dV, and it would be what? K q by L dx by x. The minimum value of x is what? A. The maximum value of x is what? X L plus a to L plus a, k q by L ln L plus a by a. This is the answer, okay. For equatorial point, how to approach? This is point P, this distance is a. How to approach? Do you remember? Small, take small element from middle point, the small element is x, okay. This is dx element. You can write dq as again q by L into dx, okay. So potential because of this point at P would be how much? K dq by the distance between them would be under root a square plus x square, okay. 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 I think the screen blacked out, so I would have to repeat a little. Somebody. So I think the camera blacked out, the screen blacked out. So I'll explain. I was at the start of this Excel point. So we have this rod here, okay, and the point P lies on its axial line. Is it okay? What we did is we took a small element dx at a distance x from point P. Okay. For dx, the charge in small element dx would be how much? Lambda dx. Okay, as you remember that lambda would be q by l for whole length, it would be q by l, for small element it would be dq by dx. And since the charge is uniformly distributed, so for small portion charge by length and for large portion charge by length is same. So we found dq, we found small potential, and we integrated, right? We took limits from the minimum value of a x would be how much? A, the maximum would be a plus l. So we took the limits from a to a plus l. The value is in terms of some log. Okay. For equatorial line, what I did, from the middle point, this is the equatorial line, right? So from the middle point at a distance x, I took a small element dx. The charge for this small element dx would be how much? Dq is equal to q by l into dx. Okay, q by l into dx. So the potential due to this would be k dq by the distance between these 2 points, the distance this hypotenuse. Okay, and for hole we would be doing what? Integrating. Obviously I won't be integrating it right now, but you know how can we integrate it? We can take x as a tan theta. We can do this kind of integration by taking x as a tan theta. Okay, so you can integrate it. Okay, the purpose of doing it is not trying to get formulas. Okay, if you are trying to memorize the formulas, by now you would have a bag full of formulas. At least in this chapter you would be having so many formulas that you won't be able to remember. The procedure, the point here is to understand the procedure, and that would be same for all the scenarios. I am trying to logically explain the procedure. Why I took dV in this scenario, in this scenario, and why am I gonna take integral E dot dr? Is it okay? I explained that as well. I'll go by that logic. So this next one, I hope you have done this. I won't be writing, won't be completing this. Okay, today you would be having a lot of homework, right? A lot of incomplete portions. Solve on your own. So the potential due to a ring. Okay, potential due to a ring. Oh, sorry. Now this is a ring. The point P is here. This is center. The radius is r. The point P is at a distance x. Is it okay? The point P is at a distance x. So which one do you think would fit better? The formula for E, if you remember, had what? The formula for E had this thing, x square plus r square ki power 3 by 2 in denominator, something something over the top, but this thing in denominator. Okay, so I won't be taking this and integrating E dot dr, calculating E dot dr. I would be doing what? Finding dV. So take small element dq here. Okay, due to this dq, the potential would be how much? This distance is r, the distance here it would be r square plus x square. So dV would be how much? K dq by this distance small r, let's call it small r, or k dq by under root r square plus x square. The whole ring is carrying charge capital Q. Is it okay? The whole ring is carrying charge capital Q. Now I didn't calculate dq here. Why? There was a particular reason. Just check. What happens is this, all points from the ring are at same distance. Don't you think? This ring is like placed like this. The point P is at the tip. Okay, So if you draw a point, the hypotenuse from here, the length would be same. If you draw the hypotenuse from, this is the ring, from side point, the length would be same. So all points on the ring would be equidistant. Is it okay? All points would be equidistant. Okay. So x distance is this. If I take dx here, this would be totally unrelated. You know, dx is generally related with x, a particle dx at a distance x, something like this. It is not related here. Okay. Plus additionally, since all the charges are all the points, they form same hypotenuse of same length with point P. So what I can do, this portion is constant, this portion is constant, I can bring them out and I can integrate directly. Getting my point? Okay. So the potential would be what? Integral dV, or it is what? This k q by under root r square plus x square. Okay. I once again repeat, if this is the ring, the point P is here. Okay. So if you draw hypotenuse from the top point, the length would be same. From side point, the length would be same. From other side point, the length would be same. So in any case, the length of hypotenuse from all the points would be same. So the denominator would be same for all the points, constant quantity, right? So I am taking it outside the integral and integrating only dq, right? So now this was for axial line. Okay. Second thing would be for center. We don't find it for any other point. For center, where x is 0. X is what? Distance from center. Distance from center is 0. So V would be kq by r. This is the maximum possible value. This is the maximum possible value on axial line. So if I plot a graph, this is the ring, this is the axial line, this is the distance x. If I plot, if I take this as origin, the graph would be like this. At center, this is maximum, okay, kq by r. On other points, it is a decreasing function, right? This is versus x. Okay, easy enough. Calculation of potential is actually a lot easier than calculation of E, because of, you know, the scalar nature. It was a vector, E was a vector, and we needed to, you know, take components, cancel them and all, lot more difficult. So potential for a ring we discussed. Let's discuss for a disk. Disk questions have shown up a lot lately, okay, 2-3 times. So potential, and that's why we need to calculate potential and field for disk. Now check, since disk has charge spread over every portion, this is, the charge is q and charge density is sigma. Okay, charge density you can find charge density would be what? Q by pi r square, the area, not difficult. Okay, the problem is that since charge is distributed everywhere, here the charge was at rim, only at the circumference. So all the points from circumference were equidistant. Now here this would be the farthest point and this would be the nearest point. The portions here would have some distance between these 2 points. I mean, like the distance would be not the minimum but not the maximum, kind of scenario, since different portions or different parts of charge are at different distances, we cannot find dV directly. What we need to do is, let's find it for a ring. Why? The reason for this is a ring. Its radius is x and its thickness is dx. Why are we doing it for a ring? The point here is that for this ring, all the points, this circumference, this hypotenuse, this hypotenuse, and all other hypotenuses are of same length. So for a ring, calculation of V is easy. We just did it. Okay. And since a disk is made up of so many rings, a ring of 0 size to a ring of capital R radius. Okay. Since our disk is made of so many rings, what we do is we integrate it after finding that for a ring. So the potential, first let's find the charge for the ring. The charge for the ring would be how much? Sigma into area of the ring. यही होगा ना? Sigma is what? Charge upon area. Sigma is charge upon area. So charge would be sigma into dA, and dA for the ring. Do you remember that what we used to do for a ring? We used to break it and open it. We used to break it and open it, and after opening it, it would form a taper kind of rectangle. Length would be 2 pi x, thickness dx. So the area of the ring would be how much? 2 pi x dx. Do you remember? So this would be sigma 2 pi x dx. So the potential due to this ring would be how much? K dq upon under root hypotenuse. K dq upon hypotenuse, which is what? If this distance, let's call this distance as small r, or no, this as x, this is r, this is r. See, a little change. In the previous question, we took this distance as x. So I am taking x, same for this question as well. The ring has radius small r and its thickness is dr. I am taking radius small r here this time, not x actually. Okay. So this would appear similar to the previous scenario. Is it okay? So now for disk, this would be the scenario. Okay. K dq upon hypotenuse, hypotenuse would be x square upon r square, and we can find it to be k 2 pi sigma r dr upon under root x square plus r square. This is dV. Okay. So V can be found by integrating dV. V can be found by integrating dV. 2 pi sigma k would come out. Okay. R is the variable, x is not the variable here. Please pay attention to this, that x is not the variable. What to do now? Take r is equal to x tan theta. यही होगा ना? And in this triangle, this is the triangle. This is x, this is r. So if I form it here, the triangle is like this. This is r, this is x. Okay. The angle would be here, formed here, theta. In this triangle, you can see that r by x would be tan theta. R would be x tan theta. So whenever I use this assumption, in physics actually, I don't know whether they do it for maths. In physics, it pays a lot if you identify the triangle as well. Okay. You already know this assumption, okay, through maths. But this kind of you can say substitution. Okay. You know this kind of substitution. So you already know the substitution, but finding the triangle here, it helps a lot. after you have done the question. Okay. So just identifying the triangle as well. You get r is equal to x tan theta. This is 2 pi sigma. K is 1 by 4 pi epsilon naught. Sigma, I'll write r is equal to x tan theta here. X tan theta dr would be x secant square theta d theta, and the denominator would be what? X square tan square theta plus x square. It would be what? X square secant square theta or x secant theta. X, so many x. So this cancels. If you find sigma by 2 pi, integral x comes out, and this would be sine theta by cos square theta d theta. Okay, writing tan and secant in terms of theta, in terms of sine theta and cos theta, right? So this thing, now you have cos theta in denominator, and its derivative exists up there. Do you remember this kind of form? This is what? Function is down here, and the power of function, sorry, power of function exists down here, and the derivative exists up. This kind of form, do you remember? याद है नहीं है? So the only thing that we need here is a minus sign. We place a minus here and a minus here. Okay? कैसे होगा अब ये? We take cos theta as t, है ना? Another substitution. So minus sin theta d theta as dt. So this integral becomes minus sigma x by 2 pi integral dt by t square. Okay, this would become minus 1 by t. Minus 1 by t. Okay, now replacing back, this would be cos theta sigma x by 2 pi. What? अच्छा, I missed epsilon actually. Sorry, 2 epsilon naught होना चाहिए था ये. So 1 by t, which would be what? 1 by cos theta. 1 by cos theta. What would be the limits? Now, the minimum value of theta would be what? 0, and the maximum value would be what? For this biggest possible triangle. Okay, the maximum value would be for this. This is the disk. This is the biggest possible triangle. This is theta naught. So the maximum value of theta would be this. Okay. So minimum for minimum theta, cos theta would be what? 1 when theta is 0. Okay. So the limits are 0 to maximum angle theta naught. Okay. For the biggest possible angle, let's find cos theta naught. Cos theta naught, this is x, this is capital R. Okay, cos theta naught would be x upon under root x square plus r square. So the answer would be sigma x upon 2 epsilon naught minus 1. If I don't know whether you are able to see it, and I don't have any space to post it as well, I'll rearrange it. Sigma x upon 2 epsilon naught 1 by cos theta 0 to theta naught, and this thing would be sigma x by 2 epsilon naught okay. You can obviously multiply x inside. You can multiply x inside, and it will get further. The formula gets a little further, changed, rearranged. So this was it. It was a little difficult one. All others won't be that difficult. They would be easier. Okay, shall we continue? Now this one is potential due to one thing that you can do, that you can really think of. I need not explain it actually. Just think about it. Whenever there is a conductor, inside the field is 0. Outside the potential, let's say on the surface, if the potential is V, it is V inside as well. You already know it. Okay. By how? By this logic, that this is E dot dr. Okay, from A to B, let's have this point A at the surface and B inside. Since E is 0, this would give me what? VB minus VA. Since E is 0, the potential difference would be 0 and VB would be equal to VA. Okay, I needed to discuss it because we would be using the same logic for conductors. Okay. Now this is potential due to a hollow sphere. This is a hollow sphere, radius r, point P is outside. Okay. Since for a hollow sphere, for an outside point, hollow sphere behaves as what? A point charge. So actually this reduces to, this is the point C, the center is C and the charge is Q. This reduces to charge Q at center C, point P as it is, the radius, the distance r as it is. Is it okay? Whole of the shell, whole of the hollow sphere or shell you can say, the shell can be squeezed and placed at center. Okay? The shell becomes a point charge placed at center and the potential becomes how much? Kq by r. So I am not actually calculating it, but we can find it. How do we understand it? The reason for that is that we know this thing. We know this thing. Okay? Infinity to r distance. Potential can be found using this. For E, if the shell behaves like a point charge, then for V as well the shell would behave like a point charge. Okay? From this formula we can see. So I am not actually solving it. Now for an inside point, let's call it X, the center C. For an inside point, since at X, ये outside के लिए था, outside, at surface first let's find. At surface V is how much? Kq by capital R. Just outside the surface, potential would be Kq by capital R because distance from center is what? This is the surface point, the distance is what? R. The potential would be Kq by R. Inside, let's find V is equal to Vx minus V, let's call this point as S, surface point. Vs is minus integral E dot dr S to x. Is it okay? The potential difference can be expressed like this. Since we know E is 0 in this scenario, inside the field is 0, RHS would be 0. So we can say that potential inside, potential at a point x inside is equal to potential at surface. So this is actually how much? KQ by R itself. Graphical interpretation becomes this. The potential is constant till surface point, after which it drops off in a rectangular hyperbola type of manner. Okay. This is for hollow sphere. Let's find for solid non-conducting uniformly charged sphere. So this is for solid non-conducting uniformly charged sphere. Oh. Now, first one is for outside. This is fully, this is a solid charged sphere, charge inside as well. Let's say it has charge Q, point P. We already know, this is center C, that even for a solid sphere, for an outside point, what can be done? Squeeze it and place at center. So even for a solid sphere, the whole charge comes at point C, the center. The distance is R, the potential is KQ by small r. Is it okay? This is easier. Second one is surface. Okay. So at surface, this is what? KQ by capital R. Again, easy job. Okay. The difficult job comes in for an inside point. So third one is inside. Okay. Now this is the sphere. Center C, radius R. Let's say I have a point here x. At what distance? Small r. Okay. Remember the basic definition? We used to bring a charge from infinity point up to this point. Okay. Do you remember? There is a problem in this kind of scenario. Why? E outside and E and inside have different formulas. So if I am trying to find V using this formula, what? Infinity to R point, where R is less than capital R. Okay. If I am trying to find V for using this formula, what I have to do? I have to integrate for outside portion and for inside portion separately. Is it okay? So now check. I would do what? Integral infinity to capital R distance, that is the surface point. I am calculating it in two stages. First, I am bringing the charge from infinity to surface point, for which the integral would be this. Then I am calculating it for by taking the charge from surface to inside. So integral how much? Capital R to small r E dot dr. Now we can actually integrate it, but we need not. Why? In the surface scenario, what we actually did, we brought the point from infinity, the charge, unit positive charge, we brought it from here to surface point. Okay. What we would have done, what we actually calculated was this thing, infinity to capital R distance, and we found it to be KQ by R. समझ आ रहा है क्या कह रहा हूँ मैं? समझ आ रहा है क्या कह रहा हूँ मैं? Okay, getting my point. You need not calculate this thing, the first term. Why? Because for outside portion you already calculated the integral KQ by R. You didn't actually calculate it, but indirectly this means the same thing. So The for outside portion the thing is kq by r, but for inside it still remains r to small r. The E here was kq small r by capital R cube. Okay, do you remember E inside was this thing? E was proportional to R, and I said okay, SHM. Okay, do you remember? So this formula. Now let's calculate the other things. They come out kq by R cube, and R dr they get integrated to form R square by 2, R square by 2, and the limits here. Okay, so I'll directly write the next step. I'll directly write the next step because there is no space remaining, right? So this thing would be 2. I am bringing 2 out, and I am putting the limits. The limits, after putting the limits, this thing would become okay. By putting, after putting the limits, this thing becomes this. And if you further solve it, because I don't have space here, I'll directly write the answer. If you further solve it, it is this. Okay, so not that difficult, I guess, but it is only because we were able to break it into 2 parts, and we knew the integral for one part. The integral for other part was not that difficult. It was RDR only. Okay, if you solve it, kq by r, take kq by r common, then take LCM and all. If you solve it, you get this only, definitely. Now let's draw it graphically. Now this is a sphere, radius r. I take its center as origin, so the graph is like this. Let's start. At center, small r is 0. First let's find at center small r is 0. So V center would be how much? 3 kq by 2 capital R. You can check. This small r square term would go. This would be 3r square by 2r cube, some cancellation. So 3 by 2 would remain. Okay, this is 1.5 times the surface value. That was kq by capital R, right? This is 1.5 times the surface value. Okay, so the maximum value would be 3 by 2 kq by R at center. On both the sides, if you check the graph, the function of V is of form this, k into a square minus r square. Okay, do you remember in quadratic equations, in those quadratic equations where the coefficient of x square was negative, what was the graph? Downward opening parabola. Do you remember that if this kind of quadratic existed, the graph was downward opening parabola? This is a similar thing. These all are constants. So V is actually dependent on minus r square. Okay, this is a quadratic equation in which the square term has negative coefficient. So this would be a negative, this would be a downward opening parabola. So a downward opening parabola which would go till this point. This point is what? The surface point. Okay, on the other side as well, surface point. Okay, the value here is kq by r, after which the formula changes. For outside point it is kq by small r only. So this, after this the formula changes. Here V is proportional to 1 by r. So the graph has 2 parts like this. Okay. Okay, let's start. I'll erase this thing. Okay, uh, in recent few years, in mains, questions from this topic have come. Okay, not last year, but I mean 2-3 years back, but not exactly this question. All know the formula. People know the formula. They can plot the graph. The question didn't ask what is the formula, potential at any inside point r. Okay, what they asked was if a portion is cut out from this. So let's solve the actual question. Let's solve the actual question. So I'll erase this thing. Is it okay? Hmm. The question is this. Also, please remember that same thing applies to gravitation as well. Same thing applies to gravitation as well. The same formula for gravitation would have become gm by 2r cube bracket में 3r square minus small r square. Is it okay? Instead of kq, we would be replacing gm. That's it. So this is a sphere out of which a small portion has been cut out. A sphere of radius r and r by 2 portion cut. The remaining portion has charge. Remaining charge. So one point is clear that you cannot apply the formula directly. Why? Q is the remaining charge. While when we were calculating, when we were deriving, we took Q as the total charge. Getting my point? Okay. We took Q as the total charge. So the formula kq by 2r cube and so on was in that Q was total charge, and out of that total charge some portion has been removed. So this is the remaining charge. So let's try to find the remaining portion would have volume how much? How much? The cutout portion, volume cut would be 4 by 3 pi r by 2 cube. So volume remaining would be how much? 4 by 3 pi r cube minus, okay, this would be 4 by 3 pi 7 by 8 r cube. Okay. So this volume has charge q, which means 4 by 3 pi r cube volume would have charge how much? How much? 8 q by 7. Just taking unitary method. I am skipping one step. That one volume would have charge how much? Q by this thing. Then this volume would have charge how much? Multiplying this. I am taking it directly. Okay. Rest of the material is here. Only 7 by 8 is extra. Just transferring it here after reversing, obviously. So this volume would have charge 8 q by 7, which means what? Q by 7 is the removed charge. Q removed is how much? Q cut actually. Charge cut is how much? Q by 7. Is it okay? Okay. So now we know total charge was 8 q by 7, out of which q by 7 was removed out and q is the remaining. Okay. Now the question asked the potential at this point. This is the center C1. This is center C. The question asked potential at C1. Okay. Now how to do? You already know. Take a big body C1, the distance is r by 2. Okay. Find the potential. In this scenario, the charge is how much? 8 q by 7. Then take a small sphere, radius r by 2, charge q by 7, subtract it. This is C1 point. Find potential here and you get the answer. Okay. So let's start. In the first step, the potential at C1 due to whole sphere would be how much? K 8 q by 7 3 r square minus r by 2 whole square upon 2r cube. Okay. Okay, this is getting my point. The charge is 8q by 7. The distance from center is r by 2. So kq 3r square minus small r square upon 2r cube. Okay. For small one, since the point is at its center, how much is the potential? 3kq by 2r, 3 by 2 kq by r. Okay. So this is 3 by 2 k, q is q by 7 upon r is r by 2. If you solve it, you would get this is r square by 4, 11. This is 4. So this would be 11 r square by 4. So this thing would be 11 by 7 kq by r. This thing would be 3 by 7 kq by r. Okay. Yeah, correct. Okay. The answer would be how much? You get the answer 8 kq by r. Is it okay? 8 by 7 kq by r. Sorry, I missed the 7 there. And this was an actual JEE question, mains, not advanced. Shall I raise? कर दूं? The other day, someone asked in the first class itself that these are two rings, Q1, Q2. Let's say the radius are different also. Q1, this is Q2 here, Q1 here. Radius R1, R2 and R1. Okay. Let's say the center is C1 and C2. You need to find the potential difference between these 2 points. Okay, potential difference between C1 and C2. So let's find the question which was asked was a little different. I'll come to that. The potential at C1 is due to potential at C1 due to the charge Q1 would be how much? This is center of R1 ring. Okay, so the potential would be k Q1 by R1. Okay, let's say the distance here is given as some d. Some distance was given, actually I don't remember the distance. The question may be asked when that the charges are different but the radii are same, or the distance is given in terms of radius. Okay, so I'm keeping those assumptions, those the values out of this question. I'm taking general values. Okay, the potential due to first ring at its own center is this. Potential due to second ring at the center at C1 is how much? For this ring you need to draw the hypotenuse, which would be what? Under root r square plus d square. So the potential would be how much? K Q2 by under root r square plus d square. This is potential C1. For ring C2, okay, potential due to first ring at C2. First ring at C2. This time you need to draw this hypotenuse. First ring at C2 would be what? K Q1 upon under root R1 square plus d square, and potential due to second ring at C2, its own center, would be what? K Q2 by R2. Okay, okay. The question asked was this: how much work would be done to take Q charge from here to here? Work done in taking charge Q from here to here. So you already know that work done would be what? So you find this, get the answer, multiply it with Q and get the answer. Okay, this was the question asked in the first class, but the potential thing has come just now. I couldn't discuss that at that point of time when you were not ready. So I guess the time is up. Okay, we'll continue. The potential thing is almost over. We'll do capacitance in the next class. Okay, and since we have worked really hard on the electrostatics, electric field and electric potential, we would be able to get through capacitance a lot easier. Okay, okay. The next chapter, current electricity, is a little smaller. So that's why I'm stealing some time out of that chapter and giving it to this chapter, because it is actually 2 chapters. Okay, as per NCERT, there are 2 chapters. So thank you all.